Hello everyone, we are Group 1. In this presentation, we'll be investigating the impact of clustering on local efficiency in social networks. To do so, we chose two graphs that fit our needs from Snap Library by Stanford University. The main motivation behind choosing such graphs is their scalable and computation-effective size. The first graph represents Deezer FM users from European countries and their mutual followers relationships between them. And the second graph represents Last.fm users from Asian countries and their mutual follower relationships between them. Both of the graphs are binary undirected graphs whose node number, edge number, and some statistics are seen in the notebook. First of all, we've read the dataset and represented their statistical features. As seen in the adjacency matrices, both graphs have lower edge density with high node number. Both graphs are simple graphs without self-connections. In the detailed version, you can notice diagonal-based communities proving clustered structure of graphs. These clusters can represent communities like family, schoolmates, and so on. In the node degree distribution, you can notice in both graphs, the lower the node degree of nodes, the higher their number is in the distribution. The node degree higher than 75 is rare for both graphs, as expected in social graphs. This is a major detail because we'll stick with the same degree distribution while generating new graphs. In section 2, we've introduced our metrics. Local efficiency is an indication for efficiency in information transfer among the immediate neighbors of ith node when ith node is removed. As seen in the equation, the shortest path distance of all pairwise neighbors for node I is calculated, and the sum of the reciprocal of shortest paths are normalized with the possible number of connections in the subgraphs that contains the immediate neighbors of node I. Clustering coefficient for a node quantifies how close its neighbors are to being a clique. It is given by the proportion of the number of closed triangles in the immediate neighbors of node I and itself by the number of possible connections between the immediate neighbors. We can see from the equations that the denominator parts are essentially the same for both of the properties. We've generated small world graphs by using Watt-Strogatz algorithm to simulate how our concepts behave. Purely random graphs exhibit a small average shortest path length along with a small clustering coefficient. Watts and Strogatz measure that, in fact, many real-world networks have a small average shortest path length, but the clustering coefficient is also significantly higher than expected by random chains. When generating the graphs, the possibilities of random rewiring of the edges were gradually increased, and it was observed how clustering and local efficiency changed as the randomness increased. Lastly, let us show you a basic example of a single node from the Karate Club graph to clarify metrics. For node 4, the neighbor subgraph contains 3 nodes, 0, 6, and 10. When 4 is disrupted, the shortest path between 0 and 6 is 1, due to immediate links between 0 and 6. However, 10 and 6 do not have a direct connection, so the shortest path is 2. As you can see, we have summed reciprocal of the shortest paths between all pairs of nodes, both 6 and 10, and 10 and 6, and normalize with the subgraph around the node number 4. In the clustering coefficient case, the node degree of 4 is again 3, which yields the same denominator. However, the number of closed triangles around node 4 is 2. In the third stage, we've tested our hypotheses. As the total number of threads of the ith node's neighbors increases, the shortest path length between the neighbor decreases and the local efficiency increases, and vice versa. This indicates that there is a linear relationship between clustering coefficient and the local efficiency. In social networks, nodes are clustered together, possibly representing a community, and the local efficiency is usually high. Random graphs exhibit a small average shortest path length. However, rewiring edges randomly breaks the clustering and increases the shortest path between immediate neighbors resulting in a low local efficiency. In this section, we investigated the clustering coefficient and local efficiency for G1, G2, and random graph simulations derived from G1 and G2. We simulate 200 random graphs. 100 of them have the same knot degree with G1, and the other 100 have the same knot degree with G2. Network X can generate a random graph for a given knot degree distribution. However, the resulting graph may end up being a multigraph, meaning there might be multiple edges between two nodes with a low probability. For the sake of simplicity, we remove the multiple edges between any pair of two nodes. Therefore, simulated graphs have exactly the same number of nodes and at most as many edges as the original graphs. So, the resulting knot degree distribution have a small variance around the anchor graph's knot degree distribution. To sum up, local efficiency and clustering coefficient have a linear relationship, as we can see in the plot. Both G1 and G2 have high clustering coefficient and local efficiency as expected. G2 has higher clustering coefficient and local efficiency due to the smaller number of nodes it has. Simulated graphs have lower clustering coefficient and local efficiency compared to the anchor graphs. Even though the simulated graphs are derived from the anchor graphs and have the same knot degree distribution, the random rewiring of the edges decreases both clustering coefficient and local efficiency. In conclusion, the existence of many clusters in a network affects local information flow positively, since within these clusters, nodes are densely connected and the shortest path lengths are small. Our results show that even though the number of nodes can be high in social networks, the local efficiency is also high due to the existence of many small clusters. Thank you for your time.